All right, we are now getting to our radioactive waste discussion. So, some elements out there are unstable. And so they turn, and it depends on how many protons they have. And they actually will. I'm going to trying to remember this off the top of my head. Maybe I should have looked it up before I started recording. They lose, I think it's a proton they lose. They'll go from like carbon 14 to like carbon 13. Um, and in that process, when it releases that proton, let me just Google real fast. I want to make sure I'm speaking right, that it is actually a proton. Half-life proton. Looks like it is protons. Then it releases radioactivity, I guess I should say. Yeah, and sometimes in that, not only will it go from like carbon 14 to 13, it will actually change into a different element. So they have half-lives, which is the measurement. This is how we do like our carbon 14 dating when we want to know how old something is. And so over a course of time, we can say it loses half of that carbon 14 over so much time. And so you can go in and measure how much is in there now, and then you can do the math to figure out how old it would be. And so here we have, if this has a half-life of 10 years, then at 5 years, you can see it would have, that should be, half-life of 1 year is B. Okay, so at 1 year, it should lose half of it. There we go. Now looking at this one, which is the 10 years, so a half-life of 10, it should be at half there. And then another half-life, so 20, it's losing half of the half, it's at a fourth. Next 10 years, it's lost half of that fourth, so it's at an eighth, and so on. And you can see the difference between the 1 year and the 10 year. Yeah, and you can have them that vary from microseconds of half-life to billions of years. Alpha, beta, and gamma rays are the type of radiation that are given off when this happens, and exposure to that can cause very bad things, from burns to cancer and all sorts of stuff. Really large doses result in death. And then we have in history were some accidents, Chernobyl and 3 Mile Island, where bad things happen, as well as like the women who glowed. That might have been Chernobyl too, when they were working on it. Anyways, not good for you. There is some uncertainty though in how much radiation exposure actually is bad for you. So if you say, okay, over your lifetime, you've been exposed to, like, kids, quiet down, this much radiation, you're having bad things happen at this point. But is it just a linear relationship that constantly, the more and more it gets worse and worse, just equally? Or is it possibly like maybe a little bit doesn't really hurt you at all until you cross a threshold, and then all of a sudden now it's really bad? Or is it the other way, that maybe a lot of little bits is really, really, really harmful up to a point, and then after that it really doesn't matter? Like we're just not really sure exactly, how much is bad for you and how much at what rate is bad for you. And then here, this is assuming it starts from 0, but what if it doesn't start to 0? And what if you actually start with some radiation exposure? What does that look like? Here are just some examples. You can look through this on your own. It's in the book of how much radiation you get from these different things. So like here we have a chest x-ray compared to in TV viewing, compared to yeah, I guess this is all kind of like normal daily stuff. So we're constantly exposed to radiation from something. I think the textbook even mentions using porcelain dishes exposes you to radiation, which I hadn't thought about, but it's because it's clay, and a lot of clay has potassium in it, and that is radioactive. So it's just kind of everywhere. Okay, so the ones with the shorter half-lives have the most risk to us because if it has like a million or a billion years of a half-life, the odds of that particle being released while we're near it are very slim. But if it has a very short half-life, then you're going to have those particles released while we're near that object. And then some are not just radioactive, but they're actually chemical poisons too. So we kind of rank them either low level or high level. Low level ones don't really require like crazy precautions or crazy disposal, but the high level ones do. Here are locations of radioactive waste types. And let me see if I can zoom that in. You can see there's actually none in Kentucky. So I don't know if that's good or bad. Maybe it's good. So we have commercial reactors here, Navy reactors at the coasts where you'd expect the Navy to be. And then commercially spent nuclear fuel storage facilities is kind of, I don't know what color that is. I can't even find that. There must not be very many. Looking in New Mexico. No, don't see it. Zooming back out. Oop. All right. And this is just showing that the types of radioactive waste, that actually most radioactive waste is the low level kind, which is good. And then of the high level kind, this is a different types where like most of this is in spent fuel. And then you have some like commercial waste, very, very small here, and then defense waste for military purposes. So what do we do with the nuclear waste? So we really depend on a multiple barrier concept, which is put as many barriers between it and people as possible. So we bury it. We use a container as well as the geology. And so here's an example, natural barriers. This is in a volcanic tuff. Which is an extrusive volcanic rock. And then here's the container that they've also built. And then it gives rock types that are really good for this. Granite, basalt, tuffs, clays, and shales. So they're really looking at very impermeable and hard rock here on salt. Actually, salt is the best one because it's not quite like it can reseal itself. It can kind of recrystallize and seal any fractures that might happen. And granite and basalt cannot do that. Clay might be able to kind of squish and fill that crack a little bit. So here it's talking about this waste isolation pilot plant. This is in New Mexico. It opened in 1999, and it is located in bedded salt that's underlain by more evaporites, although salt itself is an evaporite, and overlain by mudstone, which is like mud that's turned into rock. It's practically like a clay or a shale. And then so here we've got what it looks like on the inside, a diagram of the containers, or no, the transportation vessel here, but I doubt they're taking it out of these. And then just what it looks like and how it's been constructed. This is really all engineering and not geology. So geology would be looking at finding the good location with one of those rock types, making sure it's not faulted or in a tectonically heavy area or something like that. Mentions Yucca Mountain, which seems like it's been kind of canceled, but I guess the idea could come back, that it had been flagged at one point in time as a good spot for waste disposal based on the geology and the fact that it's in like the desert in Nevada where practically nobody lives. But it's the last few years it hasn't been funded, so I don't know if it's just been canceled. If it has, they really need to look at another spot. In the book, it says we're spending $9 billion a year in temporary storage to utility companies until we find a spot. So that should probably be, they need to make that a focus. But this Yucca Mountain was rhyolitic tough. It's an arid climate, which is something they liked about it. Because you're going to have less groundwater contamination, you're not going to have as much rain, and because it's arid, the water table is going to be really, really low. Practically nobody lives there, and it doesn't get a lot of earthquakes and stuff, and it hasn't in a very long time, and it's not expected to anytime soon. But it wasn't perfect. You can see there are some faults. So, you would investigate, well, has the fault been sealed? Is there fault gouge, which is like a clay that'll form in between the faults as the rocks are rubbing against each other, like it grinds the rocks into clay. Sometimes salt can precipitate in there, depending on the geology, although, well, if this isn't tough, I guess I wouldn't expect any salt in there. The New Mexico one, that might be able to happen. That's about it. So in here, I guess this is where they were wanting to put it. And so you can see it is in impermeable layers well above the groundwater table. And that is it for nuclear waste.